Okay, good. So you've been playing with sampling from these covariance functions and computing the marginals, which is exactly what we're doing here. Just combining a covariance function with data. So you sort of now know how to do that. But the question comes up, well, where do these parameters come from? How can you choose these parameters? Well, I did say that these Gaussian process models, oh look, I'm missing a factor of half on that, how embarrassing. So there should be a half here. I haven't noticed that before, so that means I've been embarrassing myself for years. These Gaussian process models, they're based on these covariance functions, which also have these interpretations of Mercer kernels. So kernels are widely used in machine learning, kernels, these Mercer kernels. And the interpretation in a lot of areas is that they're mapping to an infinite dimensional feature space. We're going to come back to that interpretation in the Gaussian process perspective. And then we're doing linear things in that infinite dimensional feature space. I kind of personally prefer the covariance function interpretation because it's telling me what they mean probabilistically, that it's giving me the covariance between data. But one thing that's generally considered difficult by people in the kernel world, and is actually not difficult in the Gaussian process world, is finding the parameters of these covariance functions. I mean, I say it's not difficult, it's maximum likelihood. I mean, it's difficult in that you can have multiple optima, that you need to do some sort of nonlinear optimization. It's not trivial, like solving these linear algebraic setups, but it's not unknown how one should go about doing it, or one of the ways to go about doing it. And that's just to maximize the marginal likelihood. So we've already seen this approach when I sort of talked about Bayesian inference. I said I don't like the terms likelihood and prior, because at the end you just end up with a marginal likelihood again. And then you can put priors over the parameters of this marginal likelihood. So that's another way of dealing with hyperparameters, and it's certainly a very good way. We're not going to look at that in this course. We're just going to look at what it means to maximize the marginal likelihood. So the parameters, what we've got now is a Gaussian density over y, where y is a vector, which is zero mean and covariance k. But k is constrained to take certain form. So the parameters are actually inside this covariance function. Now, if we were doing maximum likelihood in a standard Gaussian system, and k was unconstrained, then the solution's trivial. It just comes out that k is equal to y transpose. But it's badly determined because k would therefore be a rank 1 matrix. So k is equal to the covariance, the empirical covariance of your data is normally the solution for maximum likelihood here. But this is a little bit odd because the empirical covariance here is not in a row-wise feature sense, it's in a column-wise data point sense. So normally the empirical covariance I talked about earlier is take each set of the features, the input features, and take XX transpose, sum them all up. Here, the only empirical covariance going is y transpose. So one vector y, but y in the data point dimensions. Not y in the feature dimensions. Y has no feature dimensions, it's a vector. And its empirical covariance is kind of y transpose. Doesn't mean very much, but we're not going to do that fit anyway. That fit is sort of not going to give us a Gaussian that has a properly determined covariance. What we're going to do is try and fit k such that this likelihood is reduced, but by varying the parameters of the covariance function. So why does this work? Well, I want to look at the two components, missing still the factor of half. I want to look at this part here, which I see as a data fit term. It's the only bit that involves the target data. This part doesn't. And this part here, which is like a capacity control. And I want to get you to think a little bit about what these terms mean in the Gaussian while we do that as well. So we've regained the factor of half. It comes from up there and pops out here. If we take the log likelihood, which is what we normally maximize, we get two terms, minus half the log of the determinant of the covariance, and then this inner product term between the inverse covariance. So let's have a think about these two terms. If we look at the error function, so drop the constant term. So the error function, negative log likelihood, we want to minimize this guy. So we're going to look at minimization of half of the log determinant plus y transpose k inverse y. We could remove the factor of half if we wanted to. So back to that decomposition that I love of the Gaussian covariance. Why do I like that decomposition? Because it gives me a better intuition about what this ellipse looks like. So this ellipse in the two-dimensional case is giving me the shape of this Gaussian function. It's giving me the principal axis of the ellipse, lambda 1 and lambda 2. So that same decomposition I liked before, r lambda squared r transpose, where r is giving me the rotation of this basis and lambda is giving me the actual values of this basis. Now, I want to look at the capacity control term, which is the log determinant. Now, I don't think I was ever taught determinants in this way, so I had to sort of realize it myself. But if we unrotate that basis, so it's now axis aligned, then we get lambda. So not lambda squared, I'm looking at the basis itself, lambda. And I can plot lambda in this way. Lambda 1, 0, that's a vector along this axis, and 0, lambda 2, okay? Now the determinant of a matrix is the product of its eigenvalues, yeah? So that is giving us that area, okay? Now if we go to a three-dimensional matrix, we add an extra dimension coming out in the third dimension, and that gives us the volume, okay? Now, I was probably badly taught, but it kind of makes sense that that is emerging from the normalization of the Gaussian. It's a volume that's dependent on that basis. So one way of thinking about this, certainly you can think about this very easily in the 2D case, this is a square that's the same size as, well, let's go back. Oh, wrong way. It's the same size as this ellipse. It's like a square coming out here, which is defining the footprint of the Gaussian. Yeah? Makes sense that it's the normalizer is something related to area, or in a three-dimensional Gaussian it's a bit harder to think about, but it's the same thing. It's just the volume. It's the area on which the Gaussian's sitting, or that ellipse. It's the volume of that ellipse being described. So it's how many different things that Gaussian can do. It's the log of that volume. Determinants are always these volumes. To get the actual volume of the ellipse, you have to multiply by 2 pi, or to get it right for the Gaussian. So that volume also doesn't change when you do this rotation, and nor does the determinant. So as you rotate this guy around, the determinant doesn't change. So of course, what we get is not, we don't look at the determinant of r lambda, we look at the determinant of the covariance. But the determinant of the covariance is just the determinant of, so the determinant of the covariance is simply which is equal to the determinant of lambda squared, or the product of the squared eigenvalues. Yet where does it appear in the normalizer for the Gaussian? It appears with a factor of half. So it's square rooted again. So really it is just the determinant of lambda is the normalizer of this system, which is just giving you the sort of area on which this ellipse sits. So it's giving you sort of this area here. How many different things does this Gaussian believe in? So if the determinant's large, it believes in many things. If the determinant's small, it believes in very few things. Of course, the log determinant is also the entropy of the Gaussian. And entropy is related to capacity and how many different things you can control. So that things match there again. So what's going on with this square and square root? Well, if you think about it, it ensures everything's positive. If I do this basis here, if I start with this basis, what happens if lambda 2 happen to be negative and I take the product? I get an area which is negative, which is no good. So when you think about what actually goes on with the reason you take the determinant of the covariance and then square root it, that determinant of the covariance is a positive definite covariance that ensures it's positive, and then you take the square root to bring it back down to being just this area. So whenever you see that determinant term, you just know you're computing an area or a hypervolume. You're computing like a hypercube's volume. And so that's the capacity control. Now the data fit term, lambda transpose k minus 1 y. Y transpose, or lambda. upside down lambda. Y transpose k minus 1y. What's this? This is a quadratic form. Okay? So it's centered at 0. So it's not obvious that this is centered at 0, but it is centered at 0. And what you want to do is you want to minimize this term. So this term is like a well. Okay? So the term is saying, in one dimension, we would be trying to pull data down to the bottom of this well. Yeah? So one thing we could do, for example, to pull data into the bottom of the well, is we could increase lambda, make it very, very large. So that scales this parabolic thing, and then things fall in here. So this is what I'm trying to show here. You have to visualize this as a sort of a cup, yeah, parabolic cup. So we want data to be by the center. Now we can get data by the center by scaling up lambda 1 and lambda 2. And then that pushes data to 0. So that is equivalent to making the covariance really, really large, inverse covariance really, really small, this term 0. But if you do that, you pay a penalty on the volume of your coverage. Yeah? So you pay a penalty on this capacity term because you're measuring lambda 1 times lambda 2. So I mean, obviously, this is all just intuition. The model doesn't really think about all this when you fit it. But this is kind of what's going on, that you've got this data fit term which is improving the fit of the model, and simultaneously it's trading it off against a capacity control term. So how could we deal with that? Well, if we got a data point like this is the sort of thing we might like to do. We may not be able to do this sort of maneuver, but a maneuver that would make this data point closer to the origin would be to rotate that system. Okay? So that wouldn't change the capacity at all, but it would say, so what we're observing really here is a y1 and a y2 that's correlated. Yeah? So if the model, if those points were close together in X space, if it could increase the length scale, by increasing the length scale, it would effectively cause correlation to occur between those values without necessarily increasing the whole eigenvalue spectrum. It will have an eigenvalue effect on the eigenvalue spectrum. But if it's seen that they're correlated, for this one point here, it kind of wants to say that they're correlated. So this is like, it's a quadratic form, but it's the same setup as we had before when we introduced the Gaussian processes. So the model's going to try and do something like that. It's going to try and represent the correlation in the covariance. Of course, it can't do that independently of everything else. So it's not just seeing 2 data points, it's seeing 100 data points, and it's got to move these parameters around to try and trade off this capacity versus the data fit term. And that's what's going on underneath the hood, yeah? So how does that look in practice? Well, here's a little data set where I've initialized the length scale too small, and what we're plotting is blue as the capacity term and black as the data fit term. Now the data fit term is very small here now because by keeping the length scale low, it can actually get a really good data fit. It sort of says, don't know what's going on in between, but I can go right through each of the data. I'm only changing length scale to visualize this. I've set the noise values to the correct value. So I know the noise because I generated the data. And I also set the overall scale of the process. But what we're going to do here is change this length scale and see what happens to the data fit term and the capacity term. Now the data fit term is going to get worse because as we increase the length scale, it's going to start smoothing between these points rather than interpolating through them exactly. But the question is, what happens to the capacity term? Because as you change that length scale, the capacity, it's going to be able to explain fewer things, so the capacity term is going to get smaller. It's going to improve. We're missing colors on that screen. No wonder things are coming out in a funny way, because the colors. Let me just try and push these plugs in. Oh, that's it. Well, the colours have been fine on my screen, and now they're better on yours. They're not ideal. But in the red here, you see the data fit term going up. In the blue, you see the capacity term going down. So this model here, it looks pretty much linear. It can model many fewer things. Its capacity to model different data sets is lower than the model here. which can model very many things. But it can model very many things, and it can also model that data, so it's got a good data fit term. Now, the sum of those two actually has a minima. And if we stop the minima there, we'll see it's there. Yeah? So according to the marginal likelihood, that's the best value for the length scale. And I did generate this data from a data set, or from a covariance with a length scale of 1. So it is the correct value. Of course, in practice, the minima is unlikely to be bang on length scale of 1. It's probably going to be one side or the other. I'm only showing you discrete values. So that's what's going on when you try and fit the covariance function parameters. Are there questions at that point before I move on to a little example of that on real data? Yeah? So have you, hands up who's done kernel methods before? Anyone heard of kernel methods? Yeah? So they don't explain how this happens. Yeah? Because they don't have the probabilistic interpretation. So what typically happens, remember way back I said error function, n over 2 log sigma squared plus the sum of squares error. And I said people often ignore that variance term. That's the capacity term in that sense, in that setup. And it's normally thrown away in kernel methods because it can only still be there if you keep the probabilistic interpretation as this being a covariance matrix. And you can do that for Gaussian data very easily, but if you just do it, you can't do that in general. If you do the kernel trick, as they call it, you're throwing away, well, it's very difficult to sustain the probabilistic interpretation for a lot of models. So the probabilistic interpretation is thrown away with the result that you can't do this type of fitting of kernel parameters in a probabilistic way. So those are optimization models. They're not probabilistic models. This is probabilistic models, which is why we can pull these parameters out. Questions?
Well, I sort of understood the capacity penalty, but the data fit, I didn't.
Okay, let's go back and look at the data fit again. So the data fit is an unusual term because people would normally expect the data fit term would be, people would be like, oh, if your data fit term was more like this, y minus f of x squared sum over I equals 1 to n. Yeah, that's the sort of data fit term people expect to see. And indeed, that is the data fit term, but then we put a prior over f of x, which is zero mean with a Gaussian process. And once you put the prior over that, this considers all possible f of x's that are under this Gaussian process and says that the answer, if you consider the prior over x, you now recover this as your data fit term, where that's the kernel. And the kernel will also have the sigma squared in there. Now, how does that look? What I'm it's zero mean. So whereas before, the data fit would mean that we could move this guy up to here, potentially, and then collapse the variance around it down to 0 to get perfect data fit. Cool. That's like proper rainforest rain. I like that. We don't get that ability. We can't change the mean of this system anymore. We can only change the covariance. But I'm trying to illustrate here the sort of things you could do when you change the covariance. This is like a well. So the idea is these are contours, and this is 0 at the bottom. So if you're at this point here, you've minimized the data fit term. It's down to 0. You're at the bottom of the well. And the moment we're up a couple of contours, climbing up the side of the well, and we want things to be in the bottom of this energy surface. The energy surface is defined by the covariance matrix, which implicitly has this basis underlying it. Now, one way we could get the point to the bottom of the well is to increase the size of the well. So just scale up lambda 1 on lambda 2. That's trivially done by scaling up k. We just make k, multiply k by alpha, and that actually scales up lambda 1 and lambda 2 and make alpha 1000. Yeah? So that would increase the data fit. But it would do so at the expense of the capacity term. So what I'm trying to show with this bit, here's one way of increasing the data fit that has no effect on the capacity term. If we just were able to, and you can't necessarily do this because the eigenvalues are non-linearly related to the kernel function parameters. But if we were to rotate that basis in some way, we can improve the data fit So effectively, we've dropped down one contour level now, yeah? So we're lower in this hole. But we haven't changed the capacity because we just rotated the thing. And the capacity is still at lambda 1 times lambda 2. Now, the reason this is a better fit is because what's going on is this data point is at approximately 2, 2. So it's correlated between y1 and y2. And now this covariance matrix, or the quadratic form associated with it, is saying that it likes correlations. Okay? So now it's a better data fit. So there's a correlation between y1 and y2. So it's not like this where we're dealing with the mean. We're just dealing with correlations in the data. So we've seen a correlation between y1 and y2. So we move the data around. Now, why is that different to this mean? Well, bear in mind this covariance function we're using may apply to another instantiation of f of x. So we could sample a totally new data set where y1 and y2 were no longer at 2, 2. They could be at minus 2, minus 2. Yeah? A totally new data set. Now that's okay under this model because it's saying they're still correlated. We're not trying to fit f of x. If we were trying to fit f of x, we would now have to revisit f of x and fit f of x again. But we've integrated out over f of x, and we're trying to fit the prior over f of x. And the prior over f of x just says that points that close should be correlated. Does that make sense? Cool.
Yeah.
Okay.
My question was, what because the blue line was negative because the log?
Yeah. Yes. The question was there. So why does the blue line, the capacity term, go negative? Because it's the log of the volume, and if the volume's underneath 1, good question. Yeah. So I kept saying volume, 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 and then I show you something that goes negative, but it's not volume; it's the log of the volume. Yeah. So it's the log capacity, in effect, that's being measured rather than the actual capacity. So if you think about that, it also means it's the sum of the log of the eigenvalues rather than necessarily the product of the eigenvalues. Okay? Other questions? Good questions they were. Now in practice, we don't just have one parameter, we have sort of 3. And I just want to show you an example of something we've tried to look at about, a question that arises for optimization. Is there a unique optima? Well, there's no guarantee of a unique optima in this case. Very often you find there's one very strong optima, and it maybe looks like there is, but there are definitely cases where the optima isn't unique. And this is a nice example from a real data set that I worked on with my student Freddy Kalaitsis. And in this example, what we have is 6,000 genes. And what we were trying to do is tell whether each gene was signal or noise. And the way we were trying to do that was fit a Gaussian process with this exponentiated quadratic covariance. So we say y is equal to f of x plus sigma squared, right? Now f of x has an implicit scale associated with it, alpha exp minus xi, it's time in this case, that's the input, ti minus tj squared over length scale squared. Yeah? So this is like a scale. So I can actually move this scale out. I can just put it there if I like. Well, it's square root of alpha, it should be. And epsilon has a scale, which is like sigma. So what we're interested in doing, I'm just pulling out these parameters from their covariances. So I'm scaling the Gaussians associated with them and saying, let me pull that parameter out. So underlying this is marginally variance 1, this is marginally variance 1, because the diagonal of this is 1, and the diagonal of this is 1. Now, if we look at this as a noise, and this as a signal, we can say, what's the signal to noise ratio of this system? Yeah? And so we might want to look at gene expression data, which is coming out over time, and say, is the signal here or is it noise? And that's what we did in this case. So we fit Gaussian processes to 6,000 of these data points, these gene expression measurements, and we compute effectively the signal to noise ratio. So what we actually did is we reparameterized this so that the whole thing is parameterized by signal to noise ratio, noise to signal ratio, and 1 minus signal to noise. Well, I can't think of the parameterization now. Multiplying everything by an overall scale. It's something like this. So some sort of scale on the outside. This, it turns out, we can fit analytically. And then what we do for every model in this contour plot, so this is the paper, what we do is we plot the value of this marginal likelihood for different length scales and different log 10 signal to noise ratios. So, what you see in this plot here is the value of the log likelihood for all those different length scales and signal to noise ratios. So going up here, we've got a very high signal to noise ratio. It's 1. And going down here, we've got a lower signal to noise ratio. And actually down here, it turns out there's a minima with an extremely low signal to noise ratio. So what I'm going to do is show you the solutions associated with each of these points. This is multimodal. There's an optimum here, there's an optimum here, I think there's an optimum all the way over here. So there's 3 modes. Now, how common is this, that this happens? Well, let's have a look at the data itself. So here's the data. I said to Freddie, let's find an example where it's multimodal. We've got 6,000 examples. I've, by hand, tried to create multimodal examples in the past and failed to do it with data sets of this size. But when we went through 6,000, there were probably several, but Freddie produced this one. And what we're seeing here is a solution which is the high signal to noise ratio. So it's the solution all the way up here. The noise is virtually 0. So this is a log signal to noise ratio here. So that's solution 1. Solution 2, which is this one here, is a much lower signal to noise ratio, but it still believes the significant signal. And then solution 3, which is all the way off the plot down here, log 10 SNR of minus 4.5, and a length scale of 2.9, so it's down here. It's kind of unidentifiable, the length scale. It's not just down here, it's all the way along here as well. It's like a long minima, because once you get that length scale to a certain length, it doesn't matter if you increase it anymore or not. Sorry, that's a log length scale, log 10 to length scale, so it's 10 to the 3, so it's 1,000. So it doesn't matter if it's 1,000, a million, 25 million, basically you'd get the same solution. So if we could see the minima here, it would be a long minima like this minima is a long minima like that. Okay? So there's 3 solutions, but the nice thing is that we get different likelihoods. So the likelihood of this one is minus 0.22, the likelihood of this one is minus 0.23, not much to choose between them. And the likelihood of this one is minus 2.1. So we know in this case, if we do a likelihood ratio test, which we can do in this setup, that this one is incredibly unlikely compared to either of the other 2. Now the model cannot really choose with any confidence between these 2 optima here. And in fact we have a ridge going all the way down here, which are all pretty likely. So it's just like back to the world. Here's the problem with doing everything we've done. Remember before, it's like, oh, with this polynomial solutions, we fitted these polynomial solutions, but they were all equally likely. We should average over them. Well, now we're back to the same situation again. Only this averaging is much harder to do in this case. So you have to turn to sampling. So if you did a sampler in this case, you would get a load of samples all the way down here. And it wouldn't want to choose between, those samples would be a continuum between these 2 different solutions. So neither of these, these are approximately equally likely, these 2 solutions. And all the way between them is a bunch of other solutions of very, very similar likelihood. So these parameters are not well determined along this line. So you would need to do another level of Bayesian inference. So maximum likelihood is great and it works in many, many cases. But here is a case where you would want to do something like hybrid Monte Carlo sampling to consider all these different length scales in order to get a good optima. The model doesn't want to choose between that and that. Yeah? Or any of the solutions in between. Any questions? That makes sense? So this is what I mean about when do you stop integrating out? We need to integrate out again in this case, really, in order to get a good model solution. for the answer we needed for that paper, we didn't need to integrate out because we were asking if there's signal or not. All of these solutions have signal. This other solution that doesn't have signal was clearly rejected under this. It's a separate optima, but it's much, much less likely by, you know, two bits. Sorry, 2 nats or something. So we're happy that there is signal here. But if we wanted to model this data correctly, we would want to do a Bayesian solution over those parameters. Yeah? But that's non-analytic. We can't compute the marginal likelihood in that case.
So we would say that the solution is like to put a prior over the length scale?
Yes, precisely. The solution is now to put a prior over the length scale, a prior over the noise variance. People use inverse gamma priors, and then deal with another level of Bayesian inference. The problem with that is it's all non-analytic, so you have to do sampling or something approximate in order to get it out. Okay? So we can determine these, but we can gain evidence for these different parameter things, but we can't necessarily, we can end up in the situation, the same situation we were before we started down this road of having badly determined situations. Okay, so I want to look at, we've been looking at polynomial basis functions, but let's just play with radial basis functions, fixed basis function models. So in a radial basis function model, what you have instead of a Gaussian with, instead of polynomial bases, you have a series of local bases which are centered at particular points. So here I've centered them at -4, 0, and 4. And what we say in these type of models is we'll multiply that by a weight vector, just like before, and then we can sample what these models look like. So this is just what you've been doing with polynomials, but here with this set of 3 radial basis functions. So if you've ever used a radial basis function network, this is the sort of thing you're doing. Now what we showed before is that if we take the inner product between those things, what we've just been doing in the lab, we said that the covariance function for these is phi transpose, where phi is the design matrix of these basis functions. And if you think about what that means explicitly for the kernel that we've been using, that says that the kernel is the inner product between the basis functions computed for each data point at each data point. So if we choose the radial basis function kernel like this, and I've chosen 3 here, and they're at -1, 0, and 1, we can plot that covariance function. The effective covariance function for this data. Yeah? So here, I'd sample these by sampling from W and multiplying by the basis functions. Just like you did in the lab session. Here, this would be, if I wanted to sample directly from the function, I could sample from this covariance instead. Now the interesting thing about it is it has these sort of bands like we saw for the exponentiated quadratic, but of course as we leave the area where the basis functions are, -1 and 1, we start dropping off to 0. The marginal a priori variance is 0. We see that in the samples. This is dropping off down here, and it will actually be 0 all the way up to infinity. So we didn't have that with the exponentiated quadratic. So what's going on? Well, these models are strongly related. So here's samples directly from that F. So I want to use the matrix notation to write function as we've just seen before, as you've just been doing in the lab. So again, we've got this function is equal to phi times W. And if I put the W as a Gaussian prior with a variance of alpha, I recover, because W and F are only related by an inner product, I recover what we've just been looking at in the lab. So this is another way of writing it out, that the covariance is equal to alpha phi transpose. There's the covariance matrix. And then if I want to look at any 2 points, I recover this object here. So that's what we've just been looking at. Now, I'm going back to sum notation here, because in sum notation what this says is that the covariance is alpha times the sum from k equals 1 to m of each of the basis functions. So you take each basis function, for xi and xj, multiply them together and add the result. For the radial basis function, because these are two exponentiated quadratics, that's why these things keep coming up. It's not because it's Gaussian, but when you multiply two exponentiated quadratics together, you get a new exponentiated quadratic. So this sum, because each of these bases is itself an exponentiated quadratic, this sum can be rewritten in this form here. E to the squared distance between xi and mu, the center, for each of the basis functions. So between xj and the center of the basis function, xi and the center of the basis function, add those two together, divide by the length scale, and multiply the whole thing by alpha. So with a sum over here. Now, that's the equivalent covariance matrix, a covariance function for this fixed basis function model. So you can see why it goes to 0. If mu is a long way away from either of these data points, then basically this thing will be 0. So that's why it drops to 0. But now we're faced with a choice. We need to choose the number and location of these bases. So this is an additional design thing that we don't have to do in the other covariance function. So what I want to do is consider what would happen if we uniformly space these bases over an interval from A to B. So the model I'm trying to put together now says that these basis functions, so this is where we're trying to predict. We choose a location A and we choose a location B. And then we uniformly space basis functions at some distance delta mu apart. So the number of basis functions is defined by b minus a divided by delta mu. Yeah? And so you can kind of, I hope, see where I'm going to go with this. Because once we've got the model in this form, we can take the limit as delta mu, the gap between the basis functions, goes to 0, and increase the number of basis functions. But we actually have to scale by delta mu at the front, because if we keep on adding basis functions, this effect here, which we saw the other way around for data points when we were looking at phi transpose phi, this effect, this thing scales with m. So we need to downscale. We don't want, as we add basis functions, because we're adding up more and more basis functions, things to drive off to infinity. So we multiply the outside by delta mu. So as delta mu goes down to 0, we're multiplying infinity by 0, which mathematicians don't like to do, but engineers are happy with. Yeah, so that's, in the limit, we want this thing to be finite variance as we take delta mu to 0. So once we've got it in that form, so this is just explaining how we can substitute mu k also for delta mu in here, because obviously each center now is a plus delta mu times the number of centers. Yeah. So substituting those things in, we go from this thing here, which is a sum, and also setting mu naught to be a and mu m to be b, so that we're effectively getting these things back in limits of the integral. We can take the limit so that sum is replaced by an integral. So this integral is between a and b, and it's over mu. So putting this integral in, I mean, this is actually an integral over an exponentiated quadratic form again. It's quadratic in x squared, because of all these terms are quadratic in x squared. It's quadratic in mu, but it's also got this sort of linear term in mu that sort of slightly messes things up. And performing that integral, here's the result. What we get is the covariance is equal to alpha times this guy here pops out because it's the integral between it's the integral of a Gaussian form of mu, but then we also get these two earth terms. So because this integration is between two limits a and b, the integral isn't just defined in terms of a sort of this guy. It ends up with this e to the xi minus xj squared times earth minus Earth. So that you should start recognizing looks like this exponentiated quadratic covariance. These guys have a slightly different role. What these guys do is it's Earth of B minus something related to the data, minus Earth of A minus something related to the data. So depending on, if your data's the wrong side of B, what you end up with is getting squashed down. You're multiplying this whole covariance. What you effectively, where these Earths sit is centered around A and centered around B. And they operate to squash everything out. So if you're between A and B here, if you're in this region here, these terms are 1. And you just have a regular exponentiated quadratic. But as you approach the edge here, you get an edge effect where things start to squash down and go to 0. So you see that same edge effect in the fixed basis function model we saw. But let's say, well, we've got infinite basis functions in the middle here already. Why don't we increase the limits a and b to infinity and minus infinity? And if you do that, these terms just go to 1. So if we take the limit of a and b going to infinity and minus infinity, we recover this. So I should have had, sorry, I'm missing, that should be alpha prime and alpha prime. So we get a new alpha, basically, where this should be alpha prime, and if we substitute alpha prime times the square root of pi L squared for alpha, we recover this covariance function here, which is the same as the exponentiated quadratic, only the length scale has a factor of square root of 2 in front of it. So what this is showing is that exponentiated quadratic basis function is a radial basis function model, but only with infinite basis functions spread entire way across the real line. Of course, when you look back at this covariance here and think, well, what would happen if I put more basis functions in along the real line, then you would start approaching this covariance here, yeah? So it sort of makes, it has the right feel to it. So this covariance here is actually a radial basis function network, but with infinite basis functions. Now that's one interpretation of the non-parametrics. That's why we have to go to this formulation, because there's, in the previous model here, there were 3 parameters associated with the 3 basis function. Here, there are now infinite parameters associated with the infinite basis function. So that old weight space view that you did at the beginning of this morning, you can't do it for this model anymore, because there's infinite parameters and infinite basis functions. But the advantages we gain are that we don't a priori decide where the data is. So it doesn't matter when we look at this covariance. A priori, we think that there's variance all the way across the real line. We don't get this problem of a priori thinking that there's 0 variance in these regions. And that's the sort of advantage of non-parametrics. One way of thinking about it is every time you look at a new data point, automatically basis functions are generated around it. Now you can do a different, this type of analysis I think was shown by Chris Williams for the first time in a NIPS paper on infinite neural networks, because the interpretation of what's going on here is you've got like a neural network with infinite basis functions, an RBF style neural network. But you can also do it with other type of neural networks. So here's another covariance function, and this one is based on a sum of infinite sigmoid-like functions. They're not actually sigmoids, they're cumulative Gaussians or Earths. Oh, that's not a very good sigmoid. But instead of those bases being RBFs, imagine if we had a bunch of sigmoid-like shapes, and they're centered at some location which is Gaussian distributed. So B, in this case, is the variance of that centering, and W is the variance of the prior over the weights of this sigmoid. So sigmoids normally have this sort of form, although, as I say, these aren't sigmoids. W transpose X, the minus there. So if you put a Gaussian prior over W, so plus B, I have to put B in here, and a separate Gaussian prior over B, and then we take this, the limit as we have infinite number of these sigmoids. And the reason you can do this is because even though the Gaussian prior over W and a Gaussian prior over B leads to a non-Gaussian output of this thing, when you take infinite non-Gaussians summed together, the central limit theorem applies, and then you recover something that's Gaussian. So you only have to work out the mean and variance of these objects, or mean and covariance, and sum them all together, scale them correctly, and you get a covariance function out. And this is the form of the covariance function. So it's useful. Don't be fooled by this guy here. He looks like his basis functions. But that's because of these weird properties of exponentiated quadratics. That when you multiply them together, you stay within the class of exponentiated quadratics. That doesn't happen with the functions underlying this. You end up in this arc sine form. And then here's some sample paths from this. So in this case, b is 4. So these basis functions are being told to center themselves around the origin. So you tend to get these effects at the edges where you tend to saturate. So once you're going down there, it will tend to stay there because there's no basis functions in these regions here. The Gaussian prior has got rid of them. So we haven't made it stationary again. We've kept this Gaussian prior b term in. If you drive b larger, that saturation effect goes away. So that's a different type of covariance. And then there's lots of interesting ways of making covariance matrices. So because the sum of two Gaussians is Gaussian, and the covariance of that thing is just the sum of the covariances, and this may be the major reason for representing things as a Gaussian process. If you have two functions, one with covariance k1 and one with covariance k2, and you want to know the covariance of the result, it's just the sum of the two covariance functions. So if you've got like these examples that Carl Rasmussen and Chris Williams give in their book, where you've got something occurring at a long length scale, so let's say, so they have examples about this Mauna Loa data, which is carbon dioxide parts per millions increasing over time, but then there's also some seasonal effect, and then there's also some sort of slower varying effect like this. So you're interested in diagnosing what's going on, and you can do this sort of additive model type approach to some, well, it's not really an additive model, I suppose it is for this case, but it's a generalized linear model where you sort of say that there's some long-term trend f1 plus some short-term trend f2 plus some trend that is periodic f3, and add all these things together, and you know that the covariance of the result is the covariance of the summed terms. Very nice and simple. So we were talking about, so there's different representations for Gaussian processes. There's basis function models, Kalman filters we'll see tomorrow, state space models in general, that spectral representation that we briefly discussed. I'm going to mention again in a moment, Bochner's theorem. All ways of representing what's going on in a Gaussian process. Well, maybe the main reason for, at some point, algorithmically, I should say, any of those representations may be the best. So Kalman filters are linear in time, whereas the general Gaussian process would be cubic in time. So algorithmically, you may want to go for any of those representations. But one very powerful advantage of looking at it from the covariance function perspective, from the modeling point of view, is you get this ability to just sum up functions, and you know that the result is the sum of the covariance functions. So this could be a Kalman filter. This could be a spectral filter of some description. This could be a state space model. You could add a basis function model. They all come together into the same thing, just in an additive way. And so this thing of adding covariances is very powerful. And in GPy, it's very easy to do. We've, of course, been seeing it already because we've been adding noise. Yeah? And that just means what we call epsilon, which is also, in some sense, a function. So questions about that?
So basically what you were saying is that if we have functions that have different behaviors, we can simply have kernels for those different behaviors and add them together.
Yes, absolutely. So one point some people have made is when you look at the covariance for one of these behaviors, it's not necessarily obvious what it's going to be. Like if I sort of say, certainly to the uninitiated, if I say the covariance function is t minus t j squared, you're not immediately going, oh, that's therefore infinitely differentiable. So it's good to know, and maybe that's not interpretable, but if you know the origin of it, And one of the origins is this spectral interpretation of a Gaussian filter in the spectrum. Another of the origins is an infinite number of radial basis functions. There's a few different ways of looking at this covariance function, interpreting it. Another interpretation that Maurizio and I work with is the solution to the heat equation. This covariance function has a load of interpretations. It doesn't matter which one you choose, it gives you some sort of understanding about what you're saying about the data. It's smoothly varying, infinitely differentiable. And then you compartmentalize that in there. Now your next bit might be, oh, there's something going on which is a stochastic differential equation, a linear stochastic differential equation with these parameters. Now it will lead to a stochastic differential equation happens to lead to a covariance function of this term, one particular type, Ti minus Tj. We're going to see it in a moment. This is called the OU covariance with no square. So you just add that term in. I mean, whether you knew the origin of that, or that also arises from a spectral filter, which is a Cauchy distribution. So there's various origins for that, which as long as you understand, you can now plug that one and add it in. So I think the interpretability is more about how you're sharing the variance across your function. Rather than looking at any individual covariance and going, oh, obviously that's a state space model, or oh, obviously that's this. I mean, you get familiar with these covariance functions. You can see how the correlations are decaying away, but that's on a broad scale. And these differentiability properties actually emerge from the behavior right at the peak of these covariances. So right around, if this is the distance, and you plot the covariance as a function of distance either way, the exponentiated quadratic is, the exponential is that, and the exponentiated quadratic is that. And as I understand it, it's the behavior very close to the origin that determines the differentiability. The behavior right up here, in a very, very local position. That makes sense, because you can only learn about differentials if you've got data that's very, very close together, yeah? So, while the long-term behavior is quite obvious, that if you're 2 away, you're correlated at 0.5, these interesting remarkable, infinitely differentiable behaviors really all occur up in the origin, right here. So it's not immediately obvious when you look at one of these covariances what the differential will be, I believe. Maybe it is for that, because that's not differentiable at the origin. So, okay, so this is a harder one to see. So it turns out the product of two covariances is also a covariance function. And this, we're going to see a little bit more about this perhaps tomorrow. It means something slightly different. Yeah, perhaps I don't want to say too much. I have to think more about the interpretations. But you can make a new covariance function by multiplying two existing covariance functions together. Of course, I've written these as if they're across the same space, x and x. But this could be across space, and this could be across time. That would be an additive model, a generalized additive model. And same thing here. This could be across space, and this could be across time. That's actually quite a commonly used thing. Multiply by a deterministic function. So if f of x is a Gaussian process, and g of x is a deterministic function, and then h of x is f of x times g of x, then the covariance for the result is g of x times gf of x, g of x. So that's where g of x is deterministic, not a Gaussian process. If they're both Gaussian processes, the result is not a Gaussian process. It's some nasty Wishart or chi-squared thing. But if this is deterministic, that's the result. And that's actually what was going on in the Earth thing I showed you earlier. So in the Earth thing earlier, g of x, is that true? I think that's right. I think we can interpret the Earth thing I showed you earlier as multiplying the original exponentiated quadratic as a function of that form, by a function of that form, to squash it out at the edges. So this is really useful, actually. People sort of think, oh, Gaussian processes are stationary. Well, sometimes they are. They're stationary if the covariance function is only dependent on the distance between x and x prime. They're stationary processes. But you could easily take a stationary process and make it non-stationary by just multiplying it by something either side. So, for example, if we wanted a process like this, so we start off with a Gaussian process that oscillates like this all over the place, the standard RBF, and we say, actually, we want this process to model some crazy behavior in this region that we observe, some non-stationary behavior. Well, we take the original process and we multiply it perhaps by a Gaussian, a Gaussian-like form, an exponentiated quadratic, which is 0 outside that region. Now the new process will only have activity inside this region. So it'll oscillate around here. So it actually becomes like a weird non-parametric basis function. Of course, you now have parameters of this thing. You've got to learn the center of this and the width of this, and then you've got a load of more parameters to optimize. So you're giving yourself headaches in terms of perhaps these parameters will be badly determined. But you could put this non-stationarity in, and you could use this as for change point detection or various things. So that's another sort of thing you can do. Questions about that? No? How are we doing for time? Okay. The linear covariance function, of course, we've seen. So the linear covariance function, it's an odd. I suggest you try this. It's kind of a funny thing that you build this covariance function, right? Set it up as a covariance function and then sample from it, and you will see straight lines. It's a very long-winded way of building a straight line, but it's a little bit freaky that it happens nevertheless. So it'll actually give you errors when you try and sample because the covariance is degenerate. It's not full rank. But if you just add a little bit of diagonal, then it will give you samples that look like straight lines. Of course, they're centered around 0 because I haven't added in the bias term here. Okay, so the final thing, I've written this out, is this thing Bochner's theorem, that given a positive finite Borel measure mu on the real line R, the Fourier transform of Q of u is the continuous function Q of t, blah, blah, blah. Q is continuous since for a fixed x, blah, blah, blah. The function Q is a positive definite function. That's the key. I had to take this. Have you noticed something about Wikipedia? There was this period when Wikipedia was really useful because it had all these good explanations for things. And then it's now been edited to ultimate correctness. So it's now got into the regime where you can't understand it anymore at all because any intuition that was in there has been removed and replaced with some formalization notion. So when you tell people, go and read Wikipedia on this, it's often a poor reference now. But you can always go and look at Wikipedia from 4 or 5 years ago. And then you often find a much better explanation. So this is the Wikipedia explanation from 4 or 5 years ago of Bochner's theorem. It's still reasonably involved, but it's got some of the key terms that the function q is a positive definite function, i.e. the kernel kx, x prime equals q of x prime minus x. It's a function only of the distance between x and x prime. And what this Borel measure is just a positive function in the Fourier space. So what this is saying is that if you have a positive filter in the Fourier space, any positive filter, it doesn't have to be centered at 0, it can be over here, but it should be symmetric to stop. It can be asymmetric, but then you get complex parts in your Gaussian process samples, which is fine if you want them. But generally, I mean, if you're looking at certain applications, you might want them. But in general, we don't want the complex parts. So you build symmetric positive measures. You can put any filter in Fourier space like this. You do the inverse Fourier transform of the filter, and the result of that is a kernel where Q is on the difference between x prime and x. So you've got to take the, so for example, if we do the square hat function, the fixed bandwidth, that gives us the sinc. Of course, it's sinc of t normally, but instead of t, you put sinc of x minus x prime. Yeah? Inside there. Actually, you don't need those absolute values because it's symmetric anyway. And that's a positive definite covariance. So any filter you can think of, as long as it doesn't go negative, as long as it doesn't sort of go down below the 0, that leads to a valid covariance function. The proof of this can be sketched as follows. Go and look at Wikipedia from 4 years ago if you want the proof. If you look at it today, it's actually really complicated. So Bochner's theorem, the take-home message from all this is if you come up with a filter in that space, it will give you a covariance. Now, there's a particular class of covariances which drop out of these filters. So here again is this, what I call the exponential covariance. It's the result potentially of a stochastic differential equation is one interpretation, but the interpretation I'm giving it here is it's a Fourier filter of this form. 1 over pi times 1 plus x squared. This is actually a Cauchy distribution, a very, very heavy-tailed distribution. And it's the Fourier transform of the exponential. So if you look up the Fourier transform of the exponential, you'll see it's that. And of course, therefore, the covariance is this. It's a function of x minus x prime. So these things are non-differentiable. Now, the Cauchy is a special case of a student t distribution with particular degrees of freedom parameter. If you go 1 up with the degrees of freedom parameter, you get the Matern class of covariance functions. Now this one is once differentiable, the Matern 3 over 2. So it's rougher than the exponentiated quadratic, but it's smoother than that Ornstein-Ulbeck exponential covariance. And it's associated with the whole Matern family is constructed by student t distribution-like filters in Fourier space. So if it doesn't have to be a probability, well, it has to be closed. Yeah, probability distributions will always work for doing this type of filtering. But you don't have to interpret them as probability distributions. So if I go 1 up further in terms of degrees of freedom, I get the Matern 5-2, which is 1 level smoother still. So this is twice differentiable. And if I take the degrees of freedom to infinity, the student t becomes a Gaussian, and I get the infinitely differentiable function. Now, you can take any degree of differentiability between those two extremes, in theory. In practice, as soon as the differentiability goes over about 4 or 5, it becomes totally unidentifiable between, for any practical data set. Are we really going to be able to identify, oh, this data stream we've got has got 5 derivatives, but not 6? That's extraordinary dense data you'd have to have in order to find that. So in practice, we tend to use this exponentiated quadratic, the Matern 5 over 2 and the Matern 3 over 2. You might, and then the OU if you want. You might look at the Matern 7 over 2. The reason, by the way, that these degrees of freedom parameter 5 over 2, 3 over 2, 7 over 2 is the form of these covariances is a bit more complicated if you don't go for degrees of freedom that are numbers of sort of factors of half or factorizable by half. Okay. So that's all I wanted to say for today. And what I'd like you to do now is go back to the lab sheet and start playing with gpi. Because while it's easy to write down a single covariance function and do whatever else, and start playing it with it as Gaussian processes, the reason we've got this Gaussian process framework is we want you to not be thinking about those algorithmics. We want you to be thinking about the modeling. So we're trying to build the algorithms underneath for doing all these things for you. And all you should have to specify is that my covariance function is a sum of a Matern covariance, an exponentiated quadratic covariance, and whatever else. So let's just go back to the lab sheet and I'll show you how that goes in the lab sheet. So
break if you want.
Yeah, that's a good idea, yeah. I was going to,
We have the snack outside.
It's a snack outside. That's even tempting. Okay, so what I'll just set this up to the right point in the lab sheet, and then we'll be back in 10 minutes, and then we'll have. I'll go through this very quickly in 5 minutes or so to show you the Gaussian processes with gpi. So the main thing here is we just import gpi additionally, and then we start defining covariance functions. So that exponentiated quadratic, we call it the RBF. Directly in models, and building Gaussian processes around those covariances. So break now, and we'll come back here at 10 to 5.